Hello, guys. Welcome back to our lectures. So we started last time with our introduction about AC circuits. We studied like what is an AC circuit. We said like the current and the voltage is changing, alternate with current. You know, we also studied like new elements like the resistors. I'm sorry, the inductors, the capacitors. Okay, and we said they have impedance and how this impedance will affect the current and the voltage and the phase difference between them. We also said like these AC circuits, we usually convert the sinusoidal like function into like a polar form, a complex number, that can be a polar form or a rectangular form. We learned how to do like conversion between polar and rectangular and so on. In this lecture, we're gonna start, our AC circuit analysis. Okay, how to solve an AC circuit. We studied a lot the DC and how we solve a DC with many methods, nodal, mesh, Thevenin, all such stuff. How to do that in AC analysis. Okay, so we're gonna start by some good news. That basically we can use any method we learn in DC here in AC. Okay, like we can use the nodal analysis, we can use the mesh analysis, Thevenin, Norton, Ohm's law, Kirchhoff current law, and so on. How to like reduce a parallel equivalent of two resistors. Here it will be two impedances and so on. Okay. Uh, and to make our life easy, one tip here, just replace any inductor and a capacitor with Z. Okay, that will make your life very easy. But we have some bad news. Fortunately, that dealing with complex numbers usually, error prone, difficult, time consuming, and error prone. It's doable, very doable, but you can do many mistakes. Okay. Another good news that we will not do complex numbers, manually. Although I taught you guys last time how to do that manually, but this is for your reference. But just we used calculator to do any calculation for us, although we can do it manually. The same will be with complex numbers. So although we know how to do it manually, as we learned last lecture, but we're gonna use some online free complex number calculators, to do that for us. Can do division, it can do like subtraction, whatever you want. You can do online, very fast as well, and very accurate. That's the most important. Okay. So I'm providing you here with two like websites. This one here to do the calculation for you. It can do also conversion from polar to rectangular and vice versa. But for this specifically changing or converting or transforming from rectangular to polar and vice versa, I'm using usually the second one. It's easier to use for conversion. Okay. And remember, we're gonna use all the time, as we see in DC part of this course, we're going to use our Desmos online calculator as well to do our just regular, calculations. Let's go now and solve one example. Okay, so in this example here, very simple circuit. We want to find the current I flow in that branch. And remember here, we are dealing with AC, so we will not use like capital letters. We use usually small letters. Small letters means AC. Okay. So good. We said at the beginning that we're gonna use, we can use any methods we learn in DC here in AC. So we can use mesh, we can use nodal analysis, we can use Ohm's law, any one of these. So what I'm gonna do, I'm gonna solve this circuit in two ways and leave you another way to do it yourself. So I'm gonna do Ohm's law, very simple. Nodal analysis, then leave you with mesh analysis. Okay. And I have some objective why I'm doing two methods to convince you that you can use any method. And secondly, to teach you that, to verify if your answer is correct or not, try another method and you should get like the same result and compare both, right? Okay, so let's start by Ohm's law. So solution one. Using Mr. Ohm's law. I equal to V divided by R, right? No, here in AC, it's something different. I small equal to V small over Z, because here our resistors are combined with like inductors and capacitors. So it's generally Z impedance. It can be resistor only if you are lucky, and in that case it will not be an AC circuit, or it can be AC circuit because the source is AC still, but it will be very easy to solve. Okay, good. So I equal to V over Z. So we have to find Z. Look at this circuit here. You have three branches. One branch contains the source, and the other two branches are just one branch is a capacitor, another branch is inductor and the resistor. So second tip, as we learned it in this lecture, just redraw the circuit in terms of impedance. So this branch will be an impedance for us, something like that. The middle branch, another impedance, whatever it is, most like inductor, capacitor, whatever. Then the third branch is basically the source. Let's call this is Z1, this is Z2, and this is our source V. Good. Now, these are two impedances in parallel, so we can reduce them into just one impedance Z, right? Right. So, V, and this is Mr. V. And finally, from that, and this is I, of course. So I equal to V over Z. So once we find Z and V, we can get I. But V is known, right? It's given here. Look at the circuit. Amplitude 120, phase 60. So V is actually 120, which is RMS value. Again, go back to our first lecture, introduction about AC circuit analysis, and you're going to know what meant by RMS. Angle 60. Okay, angle 60. So there is a phase shift in the voltage, as we learned in last lecture as well. Good. And it's 60 hertz. That means it's the standard outlet or the standard electricity come from your electric outlet at home. Okay. So the frequency here is 60, and we're gonna use this. That's very important information that we're gonna need. Okay. Now what is Z? So V is known. That's good. What is Z? Z is actually Z1 parallel with Z2. So if we know Z1 and Z2, then we can know Z, right? Right. So what is Z1? Z1 is the capacitor impedance, this one here. So we learned that the capacitor impedance is minus J over omega C. So minus J over omega. Omega is known, 2 by F, and F is 60 by 3.14, and 2 is constant, right? Parallel with Z2. Z2 is actually two components here. You have a resistor and I have like an inductor. So it will be R, which is the 20 ohms, plus L or J omega L, the impedance of the inductors, with the inductor J omega L. Okay? Okay, so once we know omega, we know Z1 and we know Z2, right? So Z1 equal to minus J over 2 by F, which is 60 hertz, C, which is 50 micro. And micro, you should convert it to farads, so it will be 10 to the minus 6. And don't try to do that yourself, just to go to our Desmos online calculator and do it. So let's slide here and let's do it. So I'll expand this. So that guy is minus 1 over this guy here. So minus 1 over, we have many stuff. So 2 multiplied by pi, you just try to pi, it will convert by itself. Very nice. Multiplied by the frequency, multiplied by 50, then we're going to divide by 1 million. I'm sorry, we're going to multiply by 10 to the power of minus 6. You can just, bring it to the numerator and it will be 1 million. Very simple. Very simple indeed. So, but this is 100,000, not 1 million. Yeah, now it's 1 million, 6 zeros. So this one is, Z1 is, can just bring this, that, minus J 53 point, let's check again, 052. Yeah, no, 52. This is Z1. Z2 is 20, which is the out. So we go here to the right. Yeah, 20 plus J 2 by 60, and the L is 100 multiplied by 10 to the power of minus 3. Again, we go to our Dismos online calculator and do it there. Use what you already did. So you already wrote before 2 by F, so use it. So multiplied by 100 multiplied by 10 to the power of minus 6, it's like 10 to the power of minus 1. We can, which is 0.1. So Z2 is actually 37.7. Just round the 699 to 7. Okay, plus, I'm sorry, J. Don't forget that. Okay, so we have Z1 and we have Z2. Now we can do Z. Z is actually, as we said, Z1 parallel with Z2. What we learned in the DC, multiplication over the addition. So Z1 over Z1 plus Z2. But here comes the complication of using complex numbers. Very, very, very complex. It will be very complex to do it yourself. Doable, very doable, but very complex, error prone. What we're gonna do? We're gonna use our online complex number calculator, not Dismos. Dismos for real only. So this is the the website. So let's do it. So basically we're gonna so do it, duplication, then we have like some addition here. Okay, so what is Z1? Z1 is minus J. Let's bring this down a little bit here. Minus J. So here we don't use J because in complex numbers we use I for the square root of minus 1. Okay, so this website use I, not J. Why we use J, not I, in our calculation or analysis here? Because I for us is current, so it will be very ambiguous and confusing. That's why we use J. So here we're gonna go back to our complex number standard, which is I. So minus 53 0.052 I multiplied by Z2, which is 20 plus 37.7 I, and we're gonna add them in the denominator. So we're gonna just copy and paste. Don't write it again. It will be error prone for you. We just avoid any source of error. And we're gonna change the multiplication to addition. Press calculate. That's it. You have it, my friend. And you have it in two forms, in the rectangular form and in the angular form, whatever you like. Here, we need the polar form because, as we learned last lecture, the polar form is very good to use and very easy to use in multiplication and addition. Multiplication and sub and division. And here, at the end, I is equal to V divided by Z. So this is division. So we're going to use the polar form. So Z is equal to 89.8 angle 9.3. So finally, I is equal to 120 angle 60 divided by 89.8933. And we learned last time, when you divide polar forms, you just divide the amplitude together. So 120 over 89.8, and you subtract the theta, the shifts. So 60 minus 9.3. We go back to our Desmos calculator here. We can do that very quick. 120 over 89.9 and that will be 133, and the angle is 60 minus 9.33. That's very simple. 50.67. Very nice. Very nice. Now, is this a correct answer? I know it's correct, but for you, if you solve this for the first time, you can use another method and you should get the same number again, right? So solution 2, that's what we're going to do right now. Solution 2, using nodal analysis. Okay, so let's redraw our circuit. Here is our circuit. We have like, reduce this a little bit. So in our circuit, we have like three branches like this. So Z1 here, I'm sorry, Z1 here, and Z2, and our source B. Okay, good. What we learn in node analysis in DC, we're going to apply the same, exactly the same here in DC. So first, in AC, we search for the nodes. Look for nodes. We have two nodes. This is what we learned, this one and this one. That's good. Number two, assign one of the nodes that you find as a reference, and our reference is usually ground. So assign one node as a reference, which is basically the ground. You can use this one in the top, or you can use this one at the bottom. The result will be different. The voltage at the point will be different, but the voltage differences and the current will be the same. Okay, so we usually go with the bottom as the ground. Again, you can do the opposite, that's fine. And we left off with one node only, this node, V. Let's call it V1, okay? Because our source is V. So, number 3, we apply KCL at the nodes that are not ground, not reference. So, we have only one node, which is V1. So, we're going to call this I. This is basically the question. We're going to call the current in this branch I1, call the current at that branch I2. You can assume any direction, that's fine. Okay, so we're going to apply at V1. So I equal to I1 plus I2. Again, what's entering the node equal to what's going out of the node. The number of charges entering the node equal to the number of charges going out of the node. So, but what is I1 and I2? I1 is the voltage difference across Z1, so V1 minus 0. This is the voltage difference between the two nodes terminals of Z1 divided by Z1. Plus, what is I2? Voltage difference across R2 over R2. What is the voltage difference across R2? V1 again minus 0, 0 over Z2, which is Z1 over Z1 plus 1 over 2. If we know V1 and I'm sorry, yeah, and the Z1 and Z2, we're gonna know I, right? What is V1? Actually, this is very simple because V1 is actually V. Because guys, this is one node. As we learned in our maybe first lecture in this course, any wire is just a short circuit, just a node. We don't care about the geometry or how we draw a wire. It can be drawn in any way. And all of them are just one node. So V1 is actually V, which is 120 angle 60. Okay, and what is Z1? Z1 is the reactance or the impedance of the capacitance. We know it already, minus J 53.052. What is Z2? Z2 is actually 20 plus J 37.7. Okay, good. Now let's write this down as, yeah. Now we're going to find yourself in a situation in which you have V1 in polar form and Z1 and Z2 in rectangular form. So you have to convert V both. You can convert Z1 and Z2 from rectangle to polar, or for you convert V from polar to rectangle, which is easier. Both are the same. But in this case here, if you convert V, this is just one step. If you convert Z, two steps, because you have to convert Z1 and Z2 as well. So we're gonna convert V. We're gonna go again to our online websites that do that for us. So this is the third website that I mentioned to you, which easy to convert polar to rectangle and vice versa. So enter the radius, which is 120, because I did this before, and the shift here is, or the angle is 60. We convert, it is 60 plus, yeah, what it is, yes, 60 plus 103.9. So 60 plus 103.9, and this is J. Good. Good. Now we can calculate it, right? So we can rewrite it in that way: 60 plus J 103.9 over Z1, which is minus J 53052, plus 60 plus J 103.9 divided by 20 plus J 37.7. What we're gonna do is very complex to do yourself. So we're gonna go again to our online calculators and do that there. So go back to the website that we learned in the beginning. We're gonna salvage what we have already there, right? So we have already written Z1 and Z2. So we just need to write V. Okay. So we're gonna use that. So V is 60 plus J 103.9, and we're gonna put like a bracket around V1 over Z1, and then plus, plus, not underscore. Then there is an underscore, so we should remove it. Then we can have this again, and of course we're gonna change the numerator. So the numerator now becomes this guy. Yeah, we have it from before. This is Z2, and we remove one of that. So yes, and we press calculate. That's it, my friend. Here it is, the answer in rectangular form and the polar form. So Z equal, sorry, I, not Z. Uh, 1.33, angle 50.25. Let's compare this with what we have. 1.33, and here is 50.67, and here is 50.25. Both are matching. Of course, there are some difference, but that's expected here, especially with using when you use complex numbers. Now your turn, and the homework, is to solve this circuit again, but using the mesh analysis. And of course, you have here the final answer. It's basically, the steps are different. Okay, guys, thank you very much. See you in the next lecture. Bye-bye.